Hi everyone, this video presentation is developed under the PHY210 Entrepreneurship Mind module. Our group has conceptualized an original innovation for a household item, which is the domestic gas stove, by dynamically incorporating the principles of thermophysics and rotational mechanics. Introducing the thermoburner, an original innovation designed to capture wasted thermal energy and convert it into rotational dynamics to maximize cooking efficiency. The importance of this project lies in its ability to promote environmental sustainability and economic relief for consumers by reducing food waste, lowering carbon emissions, and cutting down monthly utility costs through efficient energy harvesting.
Okay, so what is the concept of our thermoburner, which is our product? The concept of our thermoburner stove relies on manipulating the rate of heat transfer through solid materials, such as copper or aluminium, which is the metal is alloy. Understand the principle of heat transfer, whereas heat transfer is driven by the movement of thermal energy itself from higher region temperature to lower region temperature. This is actual natural flow exists until the equilibrium is achieved. So, how things work in this product? The physics mechanism in heat energy at microscopic level, when the fuel ignite, the kinetic energy of atoms at bottom plate increase. This makes the atoms at the bottom vibrating and shaking incredibly fast and violently. They will collide with the slower atoms, like bumping and crushing them while passing the energy along. For efficiency and energy loss, actually, no process is 100% efficient because some energy always lost as unusable waste heat. But we can reduce the amount of heat, QL, that escapes through the exhaust by forced hot combustion gases through tube and maximize the surface area for heat energy.
Hey guys, I will present components of NEAT relate to the eco-stove that we are currently studying. First of all, what physics-related need or concept are I studying? So, the eco-stove addresses the need for efficient energy utilization by reducing heat waste during cooking and converting part of the waste heat into useful electrical energy. In conventional stove, much of the heat produced by combustion is kept into the surrounding air without being used. They result in energy loss and lower efficiency. So, the eco-stove solved this problem by using heat efficiently for cooking, converting waste heat into electricity to charge electronic devices such as smartphones, reducing fuel consumption, and promoting sustainable and environmentally friendly energy use. So, this need is directly related to physics because it involves energy conservation, heat transfer, and energy conversion. There are two specific physics principles involved. First, the first law of thermodynamics, where the first law of thermodynamics states that energy cannot be created or destroyed, but can only be changed from one form to another. Mathematically, delta U equal to Q minus W, where Q is the heat supply to the system, delta U is the change in internal energy, W is the work done by the system. In detail, it works according to a structure. For example, when a pot is heated, heat is transferred to the pot by conduction, causing the temperature of the pot to increase. Second, heat from the pot is transferred to the food. When internal energy of the food increases, it heats up and cools. Third, generating electricity via thermoelectric generator, TEG. The temperature difference, whether cold or hot, generates an electrical voltage via the Seebeck effect. 4. The electricity produced is used to drive a fan. The fan pulls the cool part of the TEG so that the temperature difference remains high and efficient. And finally, the electricity from the TEG is fed through a charging circuit to charge the phone. The electrical energy generated by the thermoelectric generator is converted into chemical energy when stored in phone's battery. Next, the second law of thermodynamics states that heat naturally flows from a high temperature area to a low temperature area, not as an energy conversion process, although some energy is lost to the surroundings. Therefore, entropy will increase. First, heat flows from the fire to the pot. The second law of thermodynamics states that when heating a cooler pan, heat naturally flows from the hot fire to the cooler pot to be used to cook food. Second, heat is lost to the environment. The heat can escape through the walls of the stove. Hot gases escape from the top of the stove and the surrounding air. In conclusion, most of heat is transferred to the pot and some is lost to the environment. 3. Function of the microfan. The microfan supplies more oxygen to increase combustion efficiency, producing a hotter and more stable fire. This allows more heat to be transferred to the cooking pot while reducing heat loss. And lastly, thermoelectric generator. The thermoelectric generator requires a temperature difference between its hot and cold parts. Some of the heat must flow through the TEG and eventually be released to the surroundings. The inevitable heat loss is consistent with the second law of thermodynamics. The application of this physics concept in real life is very important because it increases energy efficiency, reduces environmental impact, saves fuel, and provides a reliable surge of electricity during emergencies such as power outage. Examples of application in everyday life are: first, cooking. The heat produced by combustion is efficiently transferred to the cooking pot through conduction, convection, and radiation, and reducing fuel consumption. Second, power outage. During power outage, the thermoelectric module converts waste heat into electrical energy, allowing users to charge their smartphones while cooking. And lastly, remote areas. In off-grid areas, eco-stove provide both cooking and electricity without relying on the electrical grid, making them suitable for daily use and emergency situations.
Next is approach. Now let's look at the two major branches of physics involved in our system, thermophysics and rotational mechanics. First, thermophysics focus on heat and temperature. In our system, it explains how heat is produced by the stove and transferred to the pot. This heat transfer increases the temperature of the water until it reaches boiling point. Second, rotational mechanics deals with objects that rotate or spin in our system. It applies it to the rotating part, such as the stove control or any rotating mechanism used to regulate the frame. It helps us understand how rotational motion controls the operation of the system. Together, thermophysics explains how heat is generated and transferred, while rotational mechanics explain how the rotating component functions to operate the system efficiently. This slide explains how the physics concepts are applied in our system through thermophysics and rotational mechanics. Starting with thermophysics, the main principle are conduction and thermal equilibrium. Heat produced in the combustion chamber is transferred to the hot side of the thermoelectric generator or TEG through conduction. Since heat naturally flows from a hotter region to a cooler one, a temperature difference is created across the TEG. This temperature difference generates electrical voltage, which is represented by the equation V equal to alpha delta T, where alpha is the seatback coefficient and delta T is the temperature difference. Next is the application of rotational mechanics. The electricity generated by the TEG powers the DC motor, producing torque. This torque overcomes the rotational inertia of the fan blades, causing them to spin. This relationship is expressed by the equation torque equal to I alpha, where T is the torque, I is the moment of inertia, and alpha is the angular acceleration. Once the fan reaches operating speed, it maintains angular momentum, which is given by the equation L equal to I omega, where L is the angular momentum and omega is the angular velocity. The spinning fan provides steady flow of air into a stove, which improves combustion efficiency, produces a stronger flame, and helps reduce smoke emissions. Overall, thermophysics converts heat into electrical energy, while rotational mechanics use the energy to drive the fan and improve the stove performance.
What are physical processes in smart TEG EcoStove? The smart TEG EcoStove operates through a combination of thermoelectric generator technology and biomass combustion. The stove design includes a thermoelectric generator that converts heat energy from biomass combustion into electrical energy. This process is based on the Seebeck effect, where a temperature gradient between two dissimilar conductors generates a voltage. Next mechanism in smart TEG EcoStove is heat transfer. Heat transfer can be described as the process where heat is passed from one substance to another. This process occurs because of a temperature difference between two objects, in which heat transfer from the hotter object to the colder one according to the second law of heat transmission. There are three types of heat transfer mechanism. First, conduction. Conduction is happen when materials or objects are in direct contact with each other. The particles in the warmer object have more energy and vibrate faster than those in the colder object. Second, convection. Convection is the process of heat transfer through the movement of fluid masses, where heat is carried throughout the system by the motion of the fluid. Third, radiation. Radiation is the third type of heat transfer. Unlike convection and conduction, radiation does not require a medium to travel. It can move through matter or a vacuum. So these are equations that involved in our projector. The heat transfer equation is Q equal to mc delta T, where Q is heat energy, M is mass, C is specific heat capacity, and theta is its temperature change. The second one is Seebeck voltage, where if V equal to S theta T, V is voltage produced, S is Seebeck coefficient, theta T is temperature difference between the hot and cold side. The main outcomes of our smart eco-TEG stove is that it converts waste heat from cooking into useful electricity. The electricity can power a cooling fan, LED light, or charge small electronic device. The cooling fan helps maintain a larger temperature difference across the TEG, decreasing its efficiency. Overall, the system reduces energy waste, is environmentally friendly, and is especially useful for camping, rural areas, and emergency situations.
To conclude, the thermoburner proves that standard kitchens appliances can be revolutionized through the smart application of physics. By deeply understanding market need, we managed to target a major problem that household faces daily, which is extreme heat waste and high gas costs. Through our unique approach, we successfully combine thermophysics and rotational mechanics into one brilliant system. By capturing waste heat and turning it into rotational energy for our microfan, we create a self-sustaining stove that saves energy, cut down costs, and protect the environment. Lastly, we hope our project highlights how green entrepreneurship and physics can work together to build a sustainable future. That's all from us regarding the need and approach for our innovation. Thank you for watching.